did last time was we talked a little bit about domains of logs. And we found that the domain of log of x was given by open interval 0 to infinity. So the only thing that's a valid input for a logarithmic function is the positive number. If you're going to put something into a log, it's got to be positive. You can take it if you want. Does it look new to you? All right, it's yours. So if you see something inside of a log, it has to be positive. So that means that if you want the domain of a function that involves a logarithm, you need everything inside of any logarithm to be positive. So let's set up some domain problems and talk through these. So if I ask you, if you like, this is page 102. For the domain of that top log function, 4 minus x squared, what inequality do you need to set up to find that domain? What's the thing in the log?
4 minus x or equal to 0.
Yeah, cool. Thing inside the log got to be positive. You need to solve 4 minus x squared strictly bigger than 0. And we're going to write down like 3 different inequalities, and we'll decide which one we want to actually walk out. That look like an inequality that you could make progress on solving? Yeah, we have like a strategy. Set it equal to 0. That gets you the endpoints. Now check some symbols. Or think about the fact that it's a parabola and like sketch a picture. This next one. What inequality do you need to solve if you want to find that domain? I guess it's whatever's in the log has to be bigger than 0. So to find this domain, you need to solve 1 plus x over 1 minus x strictly bigger than 0. All right. So I guess that is like, at a glance, more complicated than the one above because it's got a fraction instead of just a degree 2 polynomial. Is that still an inequality that you know how to solve? Yeah, the game is figure out where it is equal to 0. Figure out where a particle asymptote is. Those two things are the endpoints. Now check some sample points. Be careful with it. Nice. Feeling good? Last one. Log base 1/2 of the absolute value function. What inequality do you need to solve to get that?
X not equal to 0.
Oh, cool. I guess he's just giving me even the answer. All I was looking for absolute value bigger than 0. All right. So I see like 3 inequalities that we just listed. I think we have enough time on the docket today to like walk out one of them, maybe 2 of them. So let's just go through top to bottom. Which one would you like to see talked through? That degree 2 polynomial one, the false one that I just wrote? The one with the fraction, the second one I just wrote? Cool. See a decent number of hands there. The absolute value one? Okay, that seems to be more or less unanimous. All right, so let's list the steps. So if you want to solve this inequality, set the thing equal to 0 and solve. That look like an equation you know how to solve? Yeah, so like the 2 options I'll give is I'll be quiet for a bit, you'll solve it for me, or I can talk through the algebra. Anyone want me to talk through the algebra? Nice, then I'll do it. So, to figure out what seems like a reasonable bit of algebra, think about what's the most complicated thing. I think the most complicated thing is the base division. So how could you undo that division? Multiply the other side by it. So cross multiply.
Oh, cool. But what's 0 times anything? Nice. So it's just 1 plus x equals 0. So what is x? -1. Cool. All right, there's step 1. Step 2. Find the vertical asymptotes. So, look at the inequality that you want to solve. Any input that will result in division by 0 you need to worry about. What input or inputs will result in division by 0?
One in that.
Yeah. Cool. So 1 minus x equals 0. Yeah, that corresponds to x equals 1. So x equals 1 and x equals -1 are endpoints. So I'll draw myself a number line to see what sample points I need to worry about. And I will include in this number line the endpoints. So -1 came from equality. So should -1 be included or excluded? I need the thing to be strictly bigger than 0, so should I include or exclude that? Exclude. It came from equality, but I want strict inequality. X equals 1. Should that be included or excluded? Excluded. Why? I agree with the conclusion.
If x equals 1, there's no real number.
Yeah. So you'll wind up dividing by 0, which is bad. All right. So now that we have the endpoints, we need to check some sample points, right? So I need a sample point that's less than -1, a sample point between -1 and +1, and then a sample point bigger than 1. So I guess let's pick one. Give me a number that is less than -1. -2. All right. So you plug in x equals -2. You'll get -2 plus 1 over 1 minus -2. And you're just worried about whether or not that is bigger than 0 or less than 0. Which is it? One way to do it is actually computing it. Positive? Negative? Cool, I think I agree. I think it's negative a thought, but I'm not positive. Cool. All right, so that means all of the numbers to the left of -1 should either all be included or all be excluded. Which one? Include or exclude? Exclude. I want positive, not negative. All right. Do you think I can now cut you loose and you'll check some sample points on your own? Nice. Check some sample points. Maybe check in with your neighbors. Maybe break up your walk with your neighbors. There's no need for everyone to check every interval. Once you have a conclusion, go ahead and shout it out. negative 1 to 1, include or exclude? Include? Do I hear agreement? Nice. What's M want you to use? 0 seems like a good choice. Things bigger than 1, include or exclude? Does thumbs down mean exclude? Okay. Nice. Is that enough that you now know what the domain is? What interval is it? Yeah, but I want someone to like say it.
-1 to 1.
Cool. Including or excluding?
Excluding.
Cool.
So whenever you want to find the domain of something that involves some logs, you need to know what input to make that log positive. You'll wind up with an inequality to solve. It can be as complicated as an inequality can be. That feel pretty good? Nice. Last thing I want to do on this page is let's jump down to this next one. Let's combine the fact that we know what the graph of logarithmic functions look like with we know how to transform graphs to find the graph of a transformed logarithm. So let's try to sketch the graph of ln of 2x plus 1 minus 1. And I guess the thing we need to remember is like, what order do you need to deal with those transformations in? Because it matters. And what do each of the transformations do? So I see the 2 times the x, the plus 1 in the parentheses, and the minus 1 outside of the parentheses. Which of those am I supposed to deal with first or last? It was a while ago, wasn't it?
You do them inside the parentheses first.
That'll walk. That'll walk. Yeah, so the order you need to deal with things is you need to deal with that plus 1 before that times 2. And you need to deal with whatever's multiplied by the ln before you deal with that minus 1. So let's just start from the inside. That plus 1, what is it going to do to the graph? Left 1. So, in blue in this same picture, I will get ln of x plus 1. So I guess that means everything needs to be shifted to the left by 1. So where will that point go when I go left by 1? 0, 0, that's cool. Comma 1, where will that go?
E minus 1.
Yeah. E is like 2.7-ish, so it'll become 1.7-ish, comma 1. E minus 1, comma 1. There's a vertical asymptote here at x equals 0, so I guess that needs to be shifted left by 1 as well. All right, feeling pretty good? So I guess the next thing we could deal with is the 2 in front of the x. Or we could do the minus 1 first. It doesn't matter what order you do the stuff inside the parentheses versus outside. As long as you deal with the shift before that stretch and this stretch before that shift. So the 2 in front of the x first or the minus 1 first? Which would you rather? In this case, the order doesn't matter. The plus 1 first? The 2 in front of the x first. All right, I think it was like 2 to 1 out of a classroom full of like 45-ish. So that's a good turnout.
If you don't want to do them in the opposite order, do them in the opposite order. You'll get the same final answer. So this minus 1, what is it going to do to the graph? Down 1? But it's a thing that's done to output values, so it does exactly what you expect. So the next one I want is ln of x plus 1 minus 1. So that means I need to take this graph, shift it down by 1. Let's look at each of the ingredients. I have this vertical asymptote at x equals 1. Where will it go when I shift it down by 1? Stay in the same place. It'd be the same line, just down. So still have a vertical asymptote at x equals 1. This point at 0, 0, it goes to 0, negative 1. E minus 1, comma 1 will become e minus 1, comma 0. And then copy the graph down. It should look logarithmish. Pretty okay right now? All right, only thing left to do is deal with that too. ln of 2 x plus 1 minus 1. When you stick a 2 in front of the x in a function, what does it do to the graph? I guess there are two questions, horizontal and vertical, or stretch or compress. Does it do something vertical? Does it do something horizontal? Cool. Yeah, it should do something to the x values. Compress or stretch? Compress? Stretch. Nice. You know what? Because this was a while ago, let's just remind you, like, a hacky way to remind yourself. Give me a function that doesn't have to do with logs. There's a function. Has it become horizontally compressed or horizontally stretched when I did that? Compressed. Everything's gotten closer to the vertical axis. So, we need to do the same thing here. So all of the x values will get divided by 2 when I do this. So this vertical asymptote at x equals 1, where will it go? A half, right? 1 divided by 2 is, by definition, 1/2. So I'll have a vertical asymptote here at x equals 1/2. I guess that means I better extend this x-axis a little bit. Negative 1/2. It stays negative. Oh, you all just let me get away with that. That's not x equals 1, that's x equals negative 1. All right. All the x values are getting divided by 2. I see this point here at 0, negative 1. Where will it go when I divide the x value by 2? Stays put. 0 divided by 2, still 0. I see this point here at e minus 1, comma 0. Where will it go? Whatever e minus 1 divided by 2 is, comma 0. And if you want to know what e minus 1 over 2 is, well, e is like 2.7-ish, so that's 1.7-ish divided by 2. Gosh, I guess that's like somewhere between 0.8 and 0.9. And if you want more precision than that, you use a machine. Ruby. That seem all right? Nice. All right. So, having used up just shy of half of the time allotted for today, let's start on what's on the actual schedule for today. You'll notice that that's maybe a theme that I've been running with my schedule. I fall behind. Let's talk about log laws. So logarithm laws are the algebraic rules that logarithms follow.
Just like we saw a bunch of algebraic rules that exponentials follow, logs follow some laws. And I think what I want to emphasize today is what they are and how to use them rather than like where they come from. If you want to see the reason for the logarithm laws, there's an extra credit right after this section. So maybe take a look at that. Even if you go through it and you're like, you want to see why these things work out, but you just can't follow what I wrote, come talk to me at some point.
So, let's talk about logarithm laws, and let's just list them one at a time. What's the log base b of 1 for any base b? 0. Because b to the 0 is 1. Log base b of b? 1. Because the power you need to raise b to get b as the output is 1. b raised to the power 1 is b. The log of multiplication will become the sum of the logs independently. It'll become the log of x plus the log of y. So whenever you see a product of two numbers inside of a log, you could rewrite that as a sum of the logs. And whenever you see two logs added together, you can replace them with a single log of the product. And what will be much more commonly used for us today and in general is going from 2 logs to 1 log, because that'll make the equation somehow nicer to walk with. Historically, it's been really important going the other way, because this gives you a way to do multiplication if you could do addition. How many people have ever used a slide rule? How many people have ever seen a slide rule? How many people have ever heard of a slide rule? Oh, okay, that's the last one has been that one. So a slide rule, if you like, is a mechanical computing device. It's what boils down to some rulers that are attached together. You can slide one of them along and it'll give you the result of addition. That's what a slide rule is good about. If you want to do addition to high precision, you can use a slide rule to do it, just a matter of reading it off. And now it's like entirely mechanical. It's not like manipulation of symbols. It's you're physically moving something to do your addition. So why is that useful? This says if you want to multiply together two 10-digit numbers, here's what you do. You take those 2-digit numbers independently and you compute their logarithms. And you might say, well, I don't know how to do that. So you do that if you're in 40, 50 years ago, is you grab yourself your lookup table of logarithm values. It's a big old book that is just a table of log values. You flip to the right pages where those two numbers appear, you figure out what those two logs are. Now, you need to add those two numbers together. So, you add those two numbers together using your slide rule. That tells you what the log of x plus the log of y is. That's the same as the log of x times y. If you now need to know what x times y is, you grab your inverse log table lookup. That will tell you what the input is that would go to that output, just computed x times y. So that allows you to do multiplication by doing addition by passing through these logs. And that's actually the original reason that logs were developed, to do exactly that. Still useful, but not useful for the thing that I just described. Division. So if logs turn multiplication into addition, what do you think they'll turn division into? Subtraction, yeah. All right, now let's talk about exponentiation.
So when you raise something to the 5th power, that means you multiply it by itself 5 times. It's iterated multiplication. Multiplication becomes addition, so iterated multiplication should become iterated addition. What's another way of saying 7 plus 7 plus 7 plus 7 4 times? 4 times 7. It just becomes multiplication. So what this
next logarithm law says is that the log base b of x times y, x raised to the y, is y times the log base b of x. And maybe I'll emphasize, this y isn't in a log. It's just y. That feel okay? Nice. Moving on to a few more. This is one that we've used a little bit in the past because we kind of needed it to use a calculator to compute anything if you didn't have a button for different bases in your calculator. People just remember the change of base formula. The log base a of x is the same as let's use base 10. Log base a of x is the same as okay, cool. It's the same as the log of x divided by the log of a. And the way I've written it there is I gave myself space because I can put any base I want there. I don't have to use base 10. The thing inside of the parentheses becomes the thing in the log in the numerator. This a becomes the thing in the log in the denominator. And I can use any base I want on the right-hand side. I get to pick b to be whatever I want, and I can write down that equation. Sometimes base 10 is the nicest thing to use if it's like the thing that your calculator does, but that's the only thing that's nicer about base 10. So pick the base to use that's most well suited to your problem. As soon as you get into calculus, the answer to that question is almost always e. E is the nicest base if you're doing any calculus. All right, there's also a change of base formula for exponentials. If you raise a to the x power, you could rewrite that as b to the x power at a cost. Not all exponentials are literally the same, but you can write a to the x as b to the x times the log base b of a. So you can rewrite any exponential as the exponential whose base is your favorite base at the cost of multiplying by a log inside of the exponent. And let me tell you how your calculator uses these. Your calculator can use any base you want for an exponent. It can use any base you want for a log. But it doesn't think about exponentiation as iterated addition. What it is going to do is it is going to translate everything to base e, because as soon as there's an e in the base for either of these, there are nice computational techniques coming from things called Taylor polynomials that then just let the calculator compute it. So the calculator will put everything as base, and then it will use that base and easier techniques to compute. Those easier techniques are techniques that you will learn in second semester calculus. Does that feel pretty good right now? We have these tools. I've told you some things about how they've been used in the past and how they're used now technologically, but let's actually use them to just do something ourselves. So here is a computation that if you wanted to do right now, what would you do? Well, you just have to ask the calculator, what's the log base 3 of 2? What's the log base 3 of 1.5? And then you'd add them together. And there would be whatever rounding error you get. We can compute this exactly on the nose without a machine. And here's how I'll propose doing it. Let's change that into a single log. So let's just take a look at that and see if any of these rules look useful. Does that rule look useful to this problem? This one? That one? I see two logs added together. Let's just see what happens when I write them as a single log. So this will become the log base 3 of what's going to be inside of the parentheses? 2 multiplied by 1.5. And 2 times 1.5 is something you can compute without a machine. What is 2 times 1.5? 3. Nice. So this is the log base 3 of 3. Oh, do one of the logarithm laws written down just tell you what that is? Yeah. It is the log base b of b with b equals 3, but that formula holds for every b. So what is this equal to? 1. Nice. And let's do a quick numerical experiment. Take out your calculator, and I think I'm going to try to rig it so that there's a higher chance of failure. Tell me, what is the log base 3 of 2 using your calculator?
3 of 2.
Log base 3 of 2. This one. Give me like just up to the 10th place.
0.6.
0.6. What about the log base 3 of 1.5? Say louder. Okay, so it added up correctly on the nose. Let's see what happens if we go one more digit. Go one more digit, does the rounding get screwed up? Actually, I think, no, it won't ever. I think 3 things to get the rounding screwed up. Anywho, this tells you what it is on the nose. The calculator will only ever be approximate. All right. Let's use this. Oh no, there's another one in this list. So I just did one. Now I want you to do one. Do you think using similar techniques you could compute for me the log base 5 of 15 minus the log base 5 of 30? In fact, I think some of you have already. I agree that that's the right answer. As you look at this, does anyone struggle to see how to start and want me to say anything? Cool. Then I'll wait till there's more or less agreement. I've already seen an answer proposed. Once you come down to an answer, let me tell me what it is. I hear a second for that. All right. I think I hear some ones. Do I hear any disagreement? Cool. All right. Do I hear a call for me to do the computation? Nice. All right. So here's the payoff. Logs let you replace sums or differences of logs that are maybe more complicated looking with a single log that is sometimes easier to compute. Here's an algebraic application of it. Let's try to solve that logarithmic equation. Log base 3 of x plus the log base 3 of x plus 8 is equal to 2. So here's more or less the strategy that I'll propose. It's annoying that there are 2 different logs on the right-hand side. I would rather there just be one log on the left-hand side, because then that would be an equation in logarithmic form. I could rewrite it in exponential form, and then at least there would be no log. So let's try to follow that strategy. Is there a rule in this list that says that you can transform a sum of 2 logs into a single log? That one? Let's use that one and see what happens. So, if I want to solve this, here's a reasonable first step. Let's replace it with the log, same base, of this times that. X multiplied by x plus 8. The right-hand side I haven't done anything with. Did I apply that logarithm law correctly? Nice. And so let's just, in addition to worrying about whether or not it's correct, let's think about whether or not it's progress. The thing inside of the log is more complicated looking now. But now instead of there being 2 logs, there's only 1 log. So that's like better, I think. So if you look at that equation, how would you rewrite that so that there isn't a log anymore? Nice. You could put this thing in exponential form instead of logarithmic form. So since the base is 3, you would wind up with 3 to the power 2 equals, and you know what, let's distribute this out too. X times x plus 8, what do you get when you distribute that? X squared plus 8x. And whenever you do two steps at once, like, there's a danger of something going along, like you instead saying x squared plus 8. And that's an easy mistake to make if you're being, like, too quick. Nice. So, x squared plus 8x is equal to 9 because that's what 3 squared is. Does that look like an easier equation to solve now? In fact, does that just look like an equation you know how to solve? Cool. Solve that equation. And I'll give you the same option, like, it's a quadratic equation, so like you have tools. If you want me to do it, I'll do it. Should I be the one who does it? Cool, then I will. Those of you who are doing it on your own will have an answer along before me. In fact, how many people have already done it? Cool. All right, so x squared plus 8x equals 9. So the algorithm I have to solve a quadratic equation is get everything onto one side so it's equal to 0. And then I can factor maybe, or I can use the quadratic formula definitely. Quadratic formula will result in bigger numbers. Factoring doesn't always work. So, x squared plus 8x minus 9 equals 0. And maybe I'll just see, these are two independent questions. So the questions are, would your instinct be to do quadratic formula or try to factor? The second question is, do you want me to use the quadratic formula or try to factor? How many people would have the instinct to try to factor? How many people would default to quadratic formula? Cool. Now, second question, should I do either one? Should I try to factor? Should I use the quadratic formula? Cool. A few more hands went up. I don't know. I think this thing does factor, though. So it's monic, so I know that these will both be x's. I need these two things to multiply together to be negative 9. So one of them will be positive. The other one will be negative. I need them to multiply together to be 9 and add together to be 8. So it's a negative 9 plus 1 will be negative 8. That's the opposite of what I want. Positive 9, negative 1 will do. And it's still equal to 0. And the point of factoring is that once you have something factored and set equal to 0, it is solved. So what are the solutions to this equation? Say louder. All right. Does that agree with what other people got? So this problem was somewhat unfair in that this answer is not correct. It is what the algebra told us. But there's a weirdness here. It's a weirdness involving domains. So remember, whenever you do algebra, you might change the domain. And in this case, here's why. In order for this expression to make sense, x needs to be positive and x plus 8 needs to be positive. After we do that simplification, if both of them are negative, well, the product of two negatives is positive. So this thing has bigger domain. These two things, I think they'll both be in the domain of that. They might not be in the domain of the thing we're actually interested in. So let's just do a quick domain check. And this is a thing you should always do when you're solving something involving a log, because there's a risk that you screwed up the domain. There's a risk that the algebra screwed up the domain. So let's do a quick domain check. So let's plug in x equals negative 9 and see what we see. I will see the log base 3 of negative 9 plus the log base 3 of negative 9 plus 8, that's negative 1. Is there something bad in that? Is there a negative inside of a log? That's bad. Negative 9 is not in the domain. Sad face. All right, let's check x equals 1. X equals 1, I'll get the log base 3 of 1 plus the log base 3 of 1 plus 8 is 9.
And you know what? Those even look like things that I know how to compute. So let's compute it and even double check if the answer is correct. What's the log base theory of 1?
0.
What's the log base theory of 9? 0 plus 2 is? Is that what I want it to be?
Yep.
Awesome. So,
X equals -9 is not in the domain. X equals 1 is the only solution.
So, the point here is, even after you finish solving an equation involving logs, you should check if your solution's in the domain. Even if all your algebra is correct, your algebra might have changed domain. So let's move on down. This next one, log base 3 of x plus 2 minus log base 2. It's all log base 2 of x plus 1 equals 3. That look like we could do a similar approach? Hope so. So the same problem arises. I see 2 logs subtracted. Is there a trick I know that can turn those 2 logs into 1 log? Yeah, I think it's this one. Subtraction outside of the log becomes division in a single log. So you can combine these 2 logs into 1 log. So with that in mind, would people rather I say once, would people rather walk it out and then come together and check the answer? Would people rather do it themselves when we come together? Cool. Is there a call for me to do the walk? Seeing no hands, I will be quiet for a few minutes. I am going to set us up something to check our answer now. People coming down to something? As you do, like, compare it with the people around you. That's also going to tell me that people are feeling like comfortable or confident. 0.
-6/7.
And here are -6 divided by 7. Cool. So instead of doing it myself at all, I am going to remind you that you can always use a machine to check your walk. And here is one way. I have sketched here the graph of both sides of the equal sign. Did I type them in correctly? Cool. Not hearing any objections? The x value where they cross is the solution. -6/7. Yeah, that's like -8.5-ish, I think. In fact, if you really want to check that now, awesome. Cool, I believe that answer. So, whenever you see an equation that involves a bunch of different logs, if you could use these logarithm laws to translate into an equation with fewer logs, at the cost of making the stuff inside of the parentheses more complicated, but still algebraic, this will let you turn logarithmic equations into purely algebraic ones which you can now solve. And you know what? With 2 minutes left, let's make some partial progress on this last one. We're not going to walk it out all the way. In fact, how many people have walked out the solution to this all the way through? I saw plenty of people walking ahead. Cool. The number gets like ugly though, right?
Yes.
Yeah, okay. So the answer is not even like satisfying. So we won't walk this one out all the way. Maybe I'll put the answer here. X equals -6/7. So let's see. I guess the first thing I see here is a 2 in front of the log. It's not on the board, but at the top of the page, it's not on the board? It's not on the board. Is there a thing in your set of logarithm laws that tells you what to do with that 2? What could you do with that 2? You could put it inside as an exponent. So you get the log, base stays the same, base always stays the same, x plus 1 squared minus log 5 of x minus 1 equals 2. Oh, cool. Does that look like basically the same problem as the one we just did? At least in terms of what makes it annoying. I see 2 different logs and they're subtracted. Oh, I can divide. Log 5 of x plus 1 squared over x minus 1 equals, don't need that parenthesis, 2. And you can write it now in exponential form, x plus 1 squared over x minus 1 equals 5 to the power 2. Ooh, how many people think that at some point as they do this, they might make the mistake of instead writing something like 2 to the power 5, where I wrote 5 to the power 2? Cool. I guarantee that I'll make that mistake unintentionally at some point in class. So it's a mistake to be aware of. And this is why you check your answer at the end. Like, we got the graph of this thing to tell us that our answer was right. If our answer was wrong, one of the things I would say you should look is look for the step where you put it into exponential form. Did you put the wrong thing in the base? Because it'll screw up your answer and it's an easy mistake to make. Groovy. So we will pick up on this Wednesday. So I screwed up the Canvas page just a little bit by failing to post some homeworks. 2 of them that I failed to post are now old enough that I have posted them as like extra credit homework problems. So what will I do with those? I'll like replace your lowest appropriate category homework score with that. So if you have a homework score you don't like, then you should do it. You do. See you.
Have a good day.
You as well.